Hello. The pyramids. The pyramids are some impressive constructions, aren't they? Millions of tons of stone, and some of those stone blocks weighing over 70 tons placed high up inside them. Some of the stones were transported 800 kilometers away and then put down with incredible precision. All of this would have had to be insanely costly. I don't think these things could be described as anything but. And not only did they build one, no, they built several, sometimes on the same site. And looking at the Nile, we can see that there are well over 100 of them. Zooming further out and looking at the world, they are across several continents, all over the place. In fact, there are thousands of pyramids all over the world. So why? Why did they build these things? And also how? How did they build the biggest ones? That's what this video is all about. I don't have all the answers, but I've come up with some hypotheses, which I'd like to share with you. Let's first go through some of the existing theories, though. And let's start with the official one. The official one goes something like this. All the pyramids were almost exclusively ritualistic, religious, or symbolic in nature. They were tombs or ceremonial sites. While this has lots of proof going for it, there's also nothing to say that they weren't something else and then repurposed in that capacity later. Also, I kind of feel that the official story is a little bit too easy. You can kind of come up with your own theories and you can make up stories on how it would have some kind of symbolic purpose to it. Also, a lot of what they claim are kind of unfalsifiable unless you find a better purpose for it. And then you have the alternative theories, which I think are well-intentioned and also potentially more useful. The official might be kind of very convenient, but when you invent some kind of symbolic purpose for things, you might actually miss out on the practical purpose, and that can further inform us of technology and stuff like that in the olden days. But a lot of the alternative theories, though, they present too much certainty in my mind. None of them are completely convincing, and a lot of them are way too certain about their own conclusions that it makes me uncomfortable. But they also often contain useful information, like novel deductions, observations that nobody else has. They tell a story that elements of it might be true, stuff like that. To go through just a few of them, some say it's an electric plant. Some say it's a water pump. Some say aliens had to be involved. And some say the air shafts are aligned with the stars and the pyramids are some kind of embedment of ancient knowledge. Some say it's a nuclear power plant, because why not? And then kind of more on the New Age thing. Some say it's got something to do with electronic resonance, sound waves, stuff like that. Some say it's got to do with mixing of chemicals. And then some focus on the construction of the pyramids almost exclusively, such as the internal ramp theory by Houdin. All of these might be labeled as kooky, but with regards to my theory, all of them has been able to contribute at least something, usually. And so I do find them useful. And even my own hypothesis, which is what I'm going to present to you now, also might not be the truth. I'm definitely not claiming that it is the truth. It's a fun hypothesis based on 4 weeks of watching a lot of entertaining videos and reading some papers. But mine too might contain some elements that might have some truth to them. Who knows? Regardless, it's a lot of fun. So, all right? All right. Let's get on with it. And I think we should start with motivation. Let's start at the very bottom and build up an argument here. And I think in general, there are 3 categories of motivation that could justify building the pyramids. The first one is religion. And of course, that's the current paradigm. All evidence is interpreted in this perspective right now. Because it's so popular, and also because it's kind of boring, and especially for me who's an engineer, I say we just skip this one. I don't want to argue against it. It's definitely a possibility though. The next one is war. And the third one is about survival. And survival is one of the biggest drivers for humankind in terms of effort and development. But what possible purpose could the pyramids have in a war effort? And frankly, I don't see it. If I'm going to steelman the argument and say that they were for mixing of chemicals, then why not just build some chambers inside the bedrock? The bedrock is going to be a lot stronger than any kind of pile of rocks that you're going to build. And so I think that makes a lot more sense. So I just say nope. I don't think war has anything to do with the pyramids. And the last one is, of course, infrastructure, which is also the most popular category for alternative theories. What kind of infrastructure? Well, we do have electricity, but then again, to power exactly what? We don't have any evidence of electrical appliances or any use of electricity back then. So not only would you have to convincingly argue the fact that the pyramids were power plants, but you also had something to use the electricity for, and I don't see it. The next one is chemicals and stuff, and I kind of address this above here. And to kind of like cut the story short, so that this video isn't way too long, because it's probably going to be very long to begin with, it has to be water, I think. Water is the only thing that makes sense. It was so important, and especially in ancient Egypt, and they used it for absolutely everything. They used it to build houses, not only for cutting and grinding and polishing and doing all kinds of work with stone, but they also made mud brick and built their houses out of mud. They, of course, used it to drink and for cleaning clothes, all kinds of cleaning. They probably used it for sanitation because you need to flush stuff away. I'm going to guess they used it for dust suppression and to moisturize, air condition the air as well. That makes sense to me, using fountains and stuff like that, indoor fountains. And of course for agriculture. I think water could be said and still has almost infinite amount of uses. And so I think water is the thing that makes the most sense. But what about the Nile though? Didn't they have the Nile, at least in ancient Egypt? Yes, they had. So let's look at water sources more in general. And let's indeed start with the Nile down here. If I list all the water sources and we start by listing river, we can give several criteria to judge them by. The first is going to be volume. And definitely rivers, and especially the Nile, had volumes in spades. It would also seasonally flood, and those floods would irrigate huge plains, and it enabled agriculture on a humongous scale. It was the reason why ancient Egypt was probably the most prosperous region in the world for thousands of years. But it wasn't completely reliable. And I think this is a fact that is very important to acknowledge. Some years, and in fact sometimes several years in a row, the floods just wouldn't come, and you would have incredible famine. Also, you could actually get overflooding. If there was a lot of precipitation, a lot of rain, it would flood much more than usual, and that would of course bypass all the current infrastructure, because they built a lot of infrastructure to capitalize and maximize the yield of the floodings. They wouldn't be able to use that, and also the buildings, which might be within the overflooding zone, might be destroyed. And so, again, that would cause famine. So reliability, a problem. The next is potability. Could you actually drink it without having to treat it somehow? And even in ancient Egypt, you couldn't actually do that. You had to boil it and then maybe brew beer on it to kind of mask the scent and the taste of it. But I don't know about you, but there's only so much sewage beer that I want to ingest over a year. So that was a problem. The last one is access. Was it easy to get to and get a hold of the water? And in some ways it was, but in other ways it wasn't. I've highlighted some houses here. And yeah, you had to haul the water inland from the Nile if you wanted access to it, because the housing needed to be sufficiently uphill or away from both the flood zone and the overflood zone. They had services back then in ancient Egypt to provide the citizens with water so they could survive. They had people dedicated, like their profession was to haul water inland. But again, it's a lot of work. And if you can get some other system to get the water that you need, and maybe cleaner and better water as well, that would be good. And so the next one I want to talk about are wells. And a well, of course, is just a vertical shaft like this going into the ground, and it goes deep enough so that it touches the groundwater. And groundwater is naturally potable. It's usually filtered through the rock, through the bedrock, and then you can drink it straight from the well. It doesn't provide as much volume though, because you have to lift up all the water like this using buckets, but at least you would have access to it, usually where you were. Now that the height that you needed to lift the water could vary, and it also wasn't perfectly reliable. Sometimes even wells would dry up, and especially if they were overused. But there are certain things that you can do to mitigate this, which we'll look into after this slide. But isn't there something even better than a well? Yes, there is, and that is a spring. The groundwater flows naturally downhill like this. So if we have more houses here and we have downhill, it flows like this usually. And this layer of earth we call an aquifer. But sometimes the aquifer doesn't stay level with the ground. It doesn't follow the ground and the terrain naturally. Sometimes you have movements of the ground that pushes the aquifer up, sort of like this. This natural bend upwards that causes water to just come straight out of the ground is called an artesian spring. I think these would be extremely valuable in ancient Egypt. And so it's natural to ask, where are they? Because some of them can contribute enormous amounts of water. And of course, it's also groundwater, so it's naturally potable. And because water is coming to you instead of you having to fetch up the water, it's the most accessible thing ever. In fact, if we think about water coming out further up and then running downhill like this, we convert potential energy into kinetic energy. And if we put on a water wheel or some other device to extract energy from it, we have a lot of free work. And so not only does the water come to you, but you can make it do work for you. In fact, if the aquifer is fed by a lake much higher up, sort of like this, it's so useful that I would actually say that it's worth digging tunnels like this and creating artificial springs. That's how useful they would have been. But even springs have problems though, which we'll also look into further along into this video. But overall though, springs, I think, are just the best thing ever. Next, let's see how we can improve these. Well design. So the basic design of a well is the word vertical shaft that looks like this. You need to haul the water up, and the water level inside the well can oscillate up and down, and sometimes it's so low that they dry up and you can overuse the well and stuff like that. So it's a lot of work and it can dry up. So it has its limitations. So let's look at what we can do to improve the design of a well. And I think the first instinctual thing is to include some sort of passive reservoir to it. So let me draw this out for you. So you have like a normal spring here, and then you also dig an additional basin next to it. When the water level in the ground raises above a certain minimum limit, the water spills over the edge and then fills up this basin. This, on average, means that you have more stability. You have an additional reservoir of water you can extract from, even if the well dries up temporarily. And on average, it's going to be less work for you because the distance, while the well goes down, you're still going to have a higher level in your reservoir. And so on average, it's going to be less work for you. But you do have this minimum that you need to reach before you start filling it up. And also, you have the opposite problem. There's a maximum here too. If you fill it beyond the minimum, when the water pressure and the groundwater level goes down again, it's going to flow out, and then you're only going to be able to maintain that minimum amount. So you have both a minimum and a maximum. So then the natural next step is, well, can we fix this? Do we have a better design? Yes. And the only thing we need to do is that we need to include a check valve. So let me draw this out for you. A check valve is essentially a one-way valve. Water can only flow in one direction. And in this case, of course, it can flow into the reservoir, but not out of it. The way I've designed it here, which is the most likely design, I think, that the ancient Egyptians would have used, is just a rock that would be lifted up by the water pressure, and then it would lay down again inside a groove and close itself up when water wanted to flow out of the reservoir again. Now this means that it's even less work. The average water level is going to be on average higher. You don't have any min and max anymore. That contributes. And also, it refills constantly. So that's a benefit as well. Now, can we further enhance this design somewhat? Yes, I think it makes sense, and we know this historically that they did so, is that you add a diagonal passage, like so. This allows you to construct the reservoir easier by having rocks pushed up or pulled up the diagonal passage instead of hauling them up vertically, which can be risky. It also allows you to, like, easier construction, there you go, and easier extraction of the water itself. You can have carts, or you can just walk down to the water surface and use buckets there instead of having to use a rope to haul it up. So in general, I think this is just a more practical solution. It might not look exactly like the way that I have drawn it, but something like this. All of these things that I've designed so far, we do see all over the world, and they have some common negatives. The first of which is that they risk contamination. They're open to the elements, which means that dirt is going to get in, and not only is the check valve is going to get clogged up, but of course you get dirty water, and so you don't want that. You also risk overflooding. What if the water pressure inside the well exceeds the ground level and water starts spilling out of the well uncontrollably? Sort of like this. Well, since infrastructure and a lot of housing is made out of mud brick, you can easily see how this could create massive problems. You could have destruction, and yeah, it would be deeply unwanted to allow this to happen. So how can we prevent that? So let's look at well overflow. First thing I would do to my well, and let me redraw it here for you, sort of like this. It's now filled all the way up and it wants to go even further. I would put a building on top of it. And the building with some heft to it, some weight. Now the water needs to push the building away in order to escape, for the water to escape. And of course, that's going to be difficult. This would cover so that it wouldn't get contaminated and like plug it. But what about the vertical passage? We could make a even bigger building to cover both the vertical passage and the reservoir, but I think it makes sense to make a portcullis like this. Now, instead of having to expand the building massively, we can simply have a sliding door that we could close, and now we don't allow water to escape. That is kind of safer, at least. It's not completely safe, but at least safer. And we do get some control over the water source. We can open up the portcullis a little bit, although how feasible that would be when the water pressure is quite high, I don't know. I think it would be very difficult. And so in general, I think with this solution that I've just drawn here, you kind of lose access to the well. So how can we maintain access to the water? And so the next thing that I think makes sense to try is to have some sort of chimney. And let me draw this. Would kind of look like this. Now you have a relatively small chimney that you need to force up into a certain height above ground, which means that the pressure, the exit pressure of the water coming out of the chimney is going to be lower than if you took the same amount of water in the same cross-section further lower towards the ground. This would allow you to retain the water supply, although in a limited capacity. You can't extract as much water as you previously could, but at least it won't spill completely uncontrollably. You could also look into integrating some sort of flow limiter inside the chimney, maybe something looking like this, having a reasonable amount of flow at any given time. All right. Next step would be a stepped construction, I think. And this is, I'm starting to get into more and more speculative territory as this video goes along, so I hope people are aware of this. So yeah, let's just proceed. And this, I think, will be a more flexible solution, although a risky one. And let me draw this one out for you. It will kind of look like this. You can have multiple levels and multiple portcullises, allowing you to open up the one that's most appropriate to the pressure and the flow rate that you want out of your well or spring. In general, I think there would be two variants. I think the one that I've kind of sketched for you here, where you have 3 levels, I would call the single column type using portcullises. And like conceptually speaking, this is how it looks. You have many portcullises at many levels, and then you make the water travel further up before it kind of like spills over. And this spillover effect means that you get less flow rate. And so the higher up the water column is, the higher up you want to open up the portcullis to get the same amount of flow rate, because you probably have a predictable amount of usage of the water, and you want a predictable amount of water as well. The other one uses multiple columns instead, kind of like this. But here, I don't think it makes sense to use portcullises. Instead, I think you need to use some other sort of valve or mechanism. And I call these overflow valves. And let me sketch these out for you. I would design them something like this, the most basic design ever. It's simply a large block of stone in a small chamber, kind of like the antechambers that you see. Now, how does this work? Well, it works by the stone at a certain flow rate will probably move and block the exit, the outlet of the overflow valve at a certain flow rate. And then if we put these overflow valves at many levels up, you can see that first it would want to have water flowing through the -1 overflow valve. And then when the water flow becomes too much because of the increased amount of pressure, then it blocks itself off, and now water has to flow through the 0 column. And then that blocks itself off, and then it goes to number 1, and then it goes to number 2. And I'm of course speaking of the bottom right multiple columns variant here, right? Yeah. And we still need some kind of chimney, because if we don't have some sort of chimney allowing air to escape or air to enter the system, we would simply end up with a siphon. And a siphon would eliminate this height that the water needs to travel before it spills over. And so you definitely need air to enter the system, so you don't get a vacuum and you don't get that siphoning effect. All right. So the next step then is to talk about, what if we have an overflowing spring? What do we actually do when water is just gushing out of the ground completely uncontrollably? Now we can't just start building a very neat and orderly structure straight on top of the spring, the rocks and the stones will simply not stay in place. They will be pushed away by the huge amounts of water that's spilling out. And of course, this overflowing spring that might suddenly appear, it will also cause potentially a lot of destruction. If you have a lot of houses like close by, something like this. This is kind of like on top of a hill. And then water can flow over there and destroy the houses and also destroy a lot of infrastructure. It can also deplete the water source, like the lake that I drew earlier. And essentially what you're doing is that you're wasting a lot of very valuable, potable, useful water. So how do we fix this? How do we actually handle this situation? Like the first damage mitigation thing that we do is that we build some retaining walls like this. And they need to be quite the distance away from where the water is coming up. Because one, you want the water to kind of settle down and be even towards the walls so that it doesn't spill over. And also you want enough room to be able to build a large structure over the spring somehow. The next step is to construct a large channel to guide the water safely away. And so it would kind of look something like this. And then the water flows down like that. What I would also look into doing, of course, is integrating some sort of sluice system like this, as well as a large channel to be able to exploit the potential energy in the water and then haul building materials up to the site using free work. So now these buildings are safe and we can start actually closing off or at least limiting or controlling the spring itself. And I would also level the ground, of course. So how do we stop the flow? How do we actually close off the spring itself? And this is where the title of the video comes in. I think it makes sense to build a big pile of rocks. So we just start stacking rocks on top, kind of around the spring first. And then lastly, one of the last steps is that we toss rocks in the middle. And then eventually all the weight of the big pile of rocks will put enough pressure on the spring itself to stop the flow. Now we do lose the access, but at least we're not wasting all this precious water anymore. We're not depleting the source. But isn't there a better way than to just randomly stack a huge pile of stones? Can't we do it in a more systemic and a better way in general? I think we can. But how exactly do we do this? I think I would want to use many of the same solutions we already talked about when it comes to wells. If I can somehow extend the bedrock upwards, I can use those solutions. This would essentially necessitate building of a column of water like this. And of course, the column of water would need to be a certain height, and it would also need to be of a certain cross-section if we want enough to flow through it. Let's start with the height. What kind of pressures do we need to counteract? Well, if we want to completely halt the spring from flowing, we need a water column that produces a hydrostatic pressure equal to what the pressure is down at the base, at the very exit of the spring. And not an unrealistic pressure to face is something along the lines of 10 bars. For those who's got some familiarity, that means that we need a water column that is 100 meters high. Holy shit, right? That's a huge water column. For the Americans out there, that's 330 feet. That's very, very tall. And of course, because we want it to be a certain size of the water column, again, this is the cross section. Let's look at, let's say that it's 1 by 1 meter. Maybe it doesn't need to be this big, but let's just say that it is. Well, we have a problem here. And the problem is that water exerts that pressure. Water, and especially at 10 bars down at the base of the water column, is going to be exerting a huge amount of pressure and also then a huge amount of force, lateral force outwards. Drawing this on the water column itself, sort of like this, we can see that the pressure and thus the force that the water column is exerting laterally is diminishing like this. It's the largest at the base, and then it gradually weakens towards the top. How do we handle these forces? This is a huge problem. We don't have steel pipes. Instead, more or less the only solution that we have available to us is something like this. We need to use weight and friction. If we have a stone like this, it has a certain amount of weight to it. That weight bears down on the ground, which when the water pressure pushes on it, which attempts to move it using a force, friction withstands moving of that block. Of course, we need to have a lot of blocks, both stacked next to themselves and also on top of them, kind of like this, in order to counteract those immense forces that we're talking about. And the amount of rock and the amount of friction and thus the amount of weight is going to be roughly proportional, that we need is going to be roughly proportional to these arrows. And so if we draw this out, and you might have suspected what I'm on about, you get a pyramid. And that's kind of neat, I think. The optimal design to counteract those forces is actually a pyramid shape. Or, well, in actuality, it's a cone shape. But taking into account the fact that it's much easier to construct something that's square instead of circular, then a pyramid is the one that makes the most sense. So now we have a water column. That means that we can build it gradually upwards, and it's safe, and we always retain access to the water source as we build it up. And we've built a big pile of stones, big pile of rocks in a pyramid shape. And the pyramid shape is stable. It's going to be strong against those lateral forces that the water column is going to produce. And also, turns out it's actually the most economic solution to the problem. So if I was an engineer back then, I would definitely build a pyramid to counteract the hydrostatic pressures or the pressures inside the spring. Now, I want to mention that I wouldn't necessarily want the walls to be 45 degrees because the bottom layer of the pyramid is also going to have the weight of all the other rocks stacked on top of it to further increase the friction and stuff. So I don't need it to be 45 degrees. It can be a lot steeper than that. And I think the Great Pyramid is something along the lines of 51 degrees from horizontal, but it can be a lot steeper than that. I think looking at the pyramids all over the world, a lot of the pyramids are a lot steeper, and it truly makes sense. It's still going to be strong enough to withstand the forces that we're talking about. But we have the next problem, and that is going to be, how do we extract the water from the water column? So that is going to be the next thing. Safe extraction of water. So let's first look at the height. What height on the water column do we extract the water at? And if we do so at the bottom, it's going to be completely unsafe at those 10 bars of pressure. And it's also going to be exceedingly difficult to make some sort of valve that can operate at those pressures. So that's completely out the window. Looking at the top, well, we have no flow rate there. That's just out of the question. The logical compromise or the best position, just flat out, is of course a bit down. A bit down from the top, we kind of estimate where we want it, where we can construct it compared to like how can we engineer something that's going to function decently. A bit down is going to give us a decent flow rate. And also, if we find the correct position of it, we're going to ensure that even if the pressure drops a little bit, we're still going to have a decent amount of flow rate if we can control it somehow. So that makes the most sense. The next one is geometry. And just extracting the water straight out from the water column like this at a 90-degree angle using a sharp corner, that's a bad idea for several reasons. The first of which, you're going to get turbulent flow. It's going to cause a lot of restriction and problems with the flow. So to describe the difference between laminar, which is the good thing, and turbulent is where the water molecules are kind of like chaotically swirling about. You have a lot of movement not in the direction that you want. The other is laminar. This, all the water molecules are kind of traveling in the same direction, more or less. Not necessarily at the same speeds, but still, it's going to be the most efficient way of transporting water. This is less restriction. It's more predictable. Yeah. So turbulent is bad. Laminar is good. How do we fix this in our water column? There are multiple solutions, but I think maybe the simplest and the best is to construct a reservoir like this. That allows the water to exit through an inlet and then slow down inside the reservoir and then accelerate gradually out the outlet again. So that facilitates more laminar flow. And you also have more control because the water level inside the water column is not going to oscillate huge amounts because you need more water to go up and down inside the reservoir compared to just the water column, right? So you have a little bit of leeway there. So sharp corner, it's a bad idea. And a reservoir, I think, is the better idea. The last thing I want to kind of mention on this slide is the design of the valve itself. And it can be a very good solution just to have a single portcullis, something like this. It's a very simple design, but it's going to be very heavy. And also, if all the water pressure is pushing on the block of stone, well, we allied with friction earlier, but now friction is working against us. We get a lot of friction in the system. It's not a good idea, I think. A better idea, perhaps, is to use a multi-system. And I think this is kind of ingenious. You allow the second and the third one and the space between them to get filled up with water. And now you have small water columns in between them. That means that instead of having like a large differential pressure, a large delta of pressure between one side of the portcullis and the other, which pushes the portcullis against rock and causes a lot of friction, you now have more even distribution of pressure, a small delta, which causes just a little bit of friction. That means that by backfilling the portcullis system, you will have an easier time moving each individual portcullis. And of course, then you also have a safer system because you have several portcullises and all of them need to fail in order for your entire portcullis system to fail. So I think this is a better idea. But there's another thing that we need to talk about that's a huge problem in this entire system. And that's the phenomena we call water hammer. So what is water hammer? Imagine you have a pipe of water and you have a large amount of water flowing through it. That water is going to have a lot of kinetic energy. Now, if you suddenly slam the portcullis, boom, like that, down, all that energy, all that kinetic energy from the flowing water needs to go somewhere. It needs to be withheld by the stone and the structure itself. And so what you get is a huge pressure spike like this. And like you can get pressures that rise many times over what you normally expect if you don't have this phenomena, if you don't account for this phenomena. Either you need to oversize or you get damage. These are like the potential consequences of water hammers if you don't find a smarter way of fixing it, which we'll look into next. Something's going to fail, and the pressure is going to find the weak point in your system, and the weak point is going to fail. And in these systems that we've been talking about so far, I think the portcullis is usually the weak point, and the portcullis is just going to go to shit like this. It's going to fail somehow and be blown completely to smithereens. What can we do? Well, here are some of the solutions. Not all of them, I think, but some that I've been able to come up with. And there's also a lot of these solutions are being used in industry all over the place. So the first one is that we can make an overflow system, which is kind of like the chimneys that we've been looking at, right? If you have the portcullis and the portcullis slams shut, now the water just continues past the portcullis and up and pushes further up water column. But this means, of course, that you need a taller water column, which would be wasteful in terms of water. Instead of stopping the water, you allowed it to spill. You also need to design a higher column of water. It's going to be costly. This is not the way that you want to do it in general. You might incorporate some version of this, but this is not the primary thing that you want to use. So next, you can insert a buffer, and we use this all the time. And what I've designed here is a type of air buffer. Now, when the water is shut off, the water pressure and the water energy, instead of going into increasing the pressure in the water itself, it instead compresses a huge amount of air. And that acts as kind of a suspension, like a car suspension, and evens out the pressure. So it doesn't reach the same amount of peaks and destructiveness as you can see in other systems. This, though, requires an airtight chamber. And also, it's pretty critical where you place it. You can't just place it anywhere. You need to place it very close by your portcullis or where you're going to shut off the water, because you want it to absorb as much of the energy as possible. Now, the next solution I want to bring up is just plugging it. So if the portcullis is weak, well, then we can maybe make some sort of emergency system that's a lot stronger. So essentially, it can look something like this. You just have a big stone that somehow the supports of which is removed when water pressure or water flow or the entire system fills up to a certain degree. Some mechanism detects when the system has failed, when the system is gone completely out of control. And now a huge stone block from the inside plugs up the entire system from the inside. Now this, of course, is extremely hard to undo, but at least it provides you with a fail-safe so that now the entire pyramid needs to fly apart for the water to escape and start damaging infrastructure and stuff like that. The last mechanism I want to highlight is an overpressure valve. And it would look maybe something like this. Essentially, and this too would need to be placed like a buffer close by where the pressure peak is expected. But here you get water needing to lift up a huge amount of weight as soon as it reaches a certain amount of pressure and it manages to lift up this very, very heavy stone. You have an alternate path for the water to flow to avoid some of the extreme peaks of pressure that can be destructive. So now I get to perhaps one of the most fun parts. When we have all of these solutions, now let's combine them all and let's see what we get. So the first thing we do is that we have our check valve. Water is flowing in like this into our reservoir. That looks something like this, right? And now we add an air buffer inside the reservoir. But as you can see, we need to be able to set where the air buffer starts. If we don't have any air outlets, like I talked about earlier, the entire system can act as a siphon and you can get a runaway water source. What you want to do is that you want a predictable place where you introduce and allow the air to escape. And that is essentially where the air shafts come in. Let me draw in kind of like the air shafts. That goes something like this, right? As you can see, as water starts filling up the water column and then starts filling up the reservoir, when they hit and supersede the air shaft positioning, now air cannot escape anymore. You're filling up the air shafts too with water, yes, but you're also compressing the air inside the air buffer. This allows you to have that suspension element inside here before you get to the valve system that's going to be here. This is a perfect position for it because it's right before the valve system. And as you can also see, the water is kind of like flowing straight towards the air buffer instead of like pointing towards the valve system. We have a 90-degree here. That's good. And so the placement of the air shafts perfectly positioned in height to start that air buffer right above it. Where are we going to put the overpressure valve? That, of course, is going to be right above, kind of like this. And let me just like finish the roof. There we go. Now we have like a huge amount of weight that if given enough pressure, if the air buffer isn't enough anymore, the entire roof of the chamber is going to be lifted up and water is allowed to escape, kind of like this. An overflow path. And as you can see, the overflow will also fill up the valve system, the backfilling system, which will allow the portcullises to be easier to raise, which is a very neat system design, I think. One cool detail that I saw in one of the papers that I read, or one of the websites that speculate about the pyramids, is the fact that if you fill up the air shafts completely with water, that is more or less the amount of pressure that will also be needed to lift the roof of all the relieving chambers up and thus allow that overflow path to open up. That's kind of a neat detail. It's an insane amount of pressure and it's an insane amount of weight, but they kind of roughly match up. So, although that's not definitive proof that this was the function of the relieving chambers and the entire structure, I think it's a really neat observation. Not mine, but a neat observation. Of course, you can also measure the amount of pressure inside the king's chamber by measuring the water level inside the air shafts, and also the angle, as I indicated to the right here, that the water is jetting out of the air shafts. But there's one thing that we've not included yet, and that is the emergency plugging system, which, of course, is the plugging stones that we see in the Grand Gallery and the ascending passage. So let's draw those in. It's kind of like this. I've shortened the Grand Gallery here, so it's like the baby version of it, but I think you'll get the point. So you would have plugging stones kind of like this, ready to slide down and get into position down in the ascending corridor. How would I design a release system for these plugging stones? Well, I would design them like this. I would have some sort of axis of rotation here, which could allow for the rotation of an arm, sort of like this. At the end, it would have a buoyant element, like this. And now, when the Grand Gallery fills up with water, the buoyant element is going to cause this entire arm to rotate up into this position. And this kind of like small arm that's holding back the rock, it wouldn't be like designed exactly like this, but sort of like this. All right, now that would essentially eliminate the friction from the system and still allow predictable and good release of the plugging stones. And of course, if you have multiple of these further up in the Grand Gallery, the plugging stones would be released in a sequential fashion. The bottom one first as the Grand Gallery is filling up, and then the next one, and the next one. And so, as you can see, all of the previous things that I've been talking about kind of make sense when you start looking at the King's Chamber, the portcullis system, the relieving chambers, the positioning of the air shafts, the Grand Gallery, all of it. Really cool, I think. Again, this doesn't say that it's absolutely true, but I think it's a cool thing. All right. Now, let's talk about how I would construct the pyramids. And I have some thoughts here too. The first thing that strikes me immediately is when we have a spring like this that represents a huge amount of free work, then I think we should use it. And indeed, a lot of things makes more sense when you think about it in these terms. So if we have ground level here and we construct our water column straight up like this, we can kind of build a structure that looks like this, right? And if that water column like exits here and then runs into, we can have a counterweight intended to be filled with water at the top of this diagonal ramp. This will allow the counterweight to slide back and forth like this, and it can be quite tall. And the counterweight slides all the way down, and then it empties. So it fills up here, and then it empties when it comes down. And now if we route these ropes further up and we extend the structure, kind of like this, the rope can wrap around some logs here, and then go down and lift stones here, up. This would be highly reusable. You could also have a dedicated counterweight to pull the main counterweight of the counterweight system back up into position to be refilled. But essentially, this would allow you to use the potential energy in the water to haul all the stones upwards. And this could also be a part of a central shaft inside the pyramid, or a simple groove that is cut into the opposite side of the pyramid, where you enter the stones and then you lift them up in a central location. Because of course, the water column would need to approximately be at the center of the pyramid. You could potentially also do the opposite. You could use the counterweight to haul stones up, and you can fill a basket or some sort of container of water, and that would pull the rope straight downwards instead. I think it's more feasible to do it the other way around, but certainly this is also a possibility. Also, I would look into trying to use all the potential energy of the water. So while the thing that I've designed and kind of sketched up on the left of the screen right now, right? That would be kind of like the first, like the most basic level, but then I would construct perhaps a series of them like this. Now, they don't need to be right on top of each other. They can also be offset by just a few meters, if you think about the offset of the corridors of the Grand Pyramid. But they could also be offset 90 degrees, 180 degrees, or alternate in a rotational pattern around the pyramid. I don't have illustrations for this. I hope you get what I mean, though. So water, you would use this for a counterweight here. Then the water would run along a horizontal passage, essentially not wasting any potential energy. You could potentially fill up a basket, like I said, with the opposite solution, and then use it to power a counterweight again, and so on and so forth. So it would kind of like follow this zigzag pattern, which would allow you to extract all the potential energy in the water. But how do I construct the last stages of the pyramid? I would do something like this. I would use the outside of the pyramid to haul stones up the slope on the side of it, like this. How would that look like inside the pyramid? Well, if we have the counterweight here that we're going to fill with water, I would take the vertical shaft and I would kind of like swing it up and put it into a reservoir, like this, like the King's Chamber. I would make a portcullis system to dosage out the water when a counterweight is in the correct position. Then I would draw a rope up vertically like this, very reminiscent of what Houdin has proposed. But I would also use, again, perhaps sort of like Houdin has proposed, I would use an additional counterweight to reset the primary counterweight by extending the portcullis system further upwards in a smaller corridor, perhaps, right? Something like this. And this would allow the rope, the primary rope that I'm pulling stuff with, to pass all the way up to the top, the very top of the pyramid, centrally, and pull every last stone up using this system. One neat observation is that the position of the Queen's Chamber, which could actually be the Queen's shaft, is kind of perfectly positioned to be this shaft that I mentioned all the way to the left of my first illustration. So maybe both the King's Chamber and the Queen's Chamber were actually the Queen's shaft and the King's shaft, each for its individual Grand Gallery, and kind of matches up with some observations. Some could say that the King's shaft and the Queen's shaft is one and the same thing, but yeah. Anyway, thank you for watching. I'd like to recommend some YouTube channels, and that's going to be Ancient Architects Uncharted X, we have History for Granite, and also Lines in Sand. Those 4 channels are kind of like my go-tos and the best channels that I've found. They all have their pros and cons, but I've always been highly entertained by the videos that they put out. So yeah, thank you so much for watching.